Thanks very much for inviting me. It's an honor. Yeah, so this is joint work with Konstantin Matetski, who is a postdoc in Toronto and is now at Columbia, and Daniel Remenik, who also was a postdoc in Toronto and is now in Chile. Okay, so let's start with a model. So this is like the end of last session. So this is a model we have no idea how to prove anything. It's just to give some ideas. Okay, so this is the Eden model. So if you haven't heard of the Eden model before, the Eden model just means that you're on a two-dimensional lattice, and you have a seed at the origin, and then it chooses a neighbor at random and adds it to the set. And that's how the set grows. It just grows by adding neighbors at random, chosen at random. Or maybe each neighbor.
Uniform. Don't say random. Uniform.
Yes. So another way to think of it is that each neighbor joins the set at rate 1. Is that okay? I want to do that.
He will tell you independently.
Otherwise, it slows down as you're getting bigger. So if you do that, of course, at time t, it'll look like t times some shape, right? So these are just snapshots. You can look on Google. There's lots of pictures of it. Yeah, I mean, it's not. This is known that it's t times some shape, and the shape's not supposed to actually be rotationally invariant. But of course, that's not very universal. Maybe on some other lattice, it might be rotationally invariant. Of course, you can make rotationally invariant versions of it. But the universal stuff comes when you look at the fluctuations. So the important thing is that the fluctuations of this bizarre scale, t to the 1/3. So on top of this thing, you're looking at this little ch. And that thing, the size of the fluctuation there is t to the 1/3. And then there's some universal processes which govern the, if you look laterally along the edge. Okay? They actually live on a scale t to the 2/3 along the edge. And there are these universal processes. The other interesting thing is that these universal processes, here you just started with a seed. There. But if you start with a half space, then the thing would sort of march across. You'd also see the t to the 1/3, and there'd also be a universal process which lived on this t to the 2/3 scale, but it would be a different process. Okay, so that's the kind of thing we're trying to understand. Okay, and these things are supposed to be very, very universal in 1+1 dimensional interface growth. So there's an interface between two phases in 2 dimensions. Okay, so for example, there have been a lot of experiments with burning paper, which turns out to be very hard to replicate. Believe it or not, coffee stains, you might laugh, but you can go to NPR, All Things Considered, and Google KPZ and coffee stains, and there's some cool videos. It's actually real science. And maybe tumor growth. I don't know, that's a bit controversial. Bacterial colonies grow like this. Okay. Okay. Now one thing to make it easier. So by the way, the Eden model, you know, if you don't want to follow the rest of the talk, you can sit down and try to prove that there's 0 results. And one of the problems with the Eden model is that that boundary is a very yucky thing. It's not even clear what you're proving. It sort of looks like this.
I mean, they're bounds, right? They're bounds on
log. Yeah.
the lower bound.
Okay.
Log.
Okay, log. Yeah. I don't think about that. Okay. So yes, there exists bound. They're unbelievably hard to prove, and they're not anything close to the truth. Okay. It's amazing people can prove it, but okay. But so the problem with that model is it's not even the interface is just some horrible thing. It looks, you know, if you zoom in on it in the Eden model, it looks like that. You know, what are you proving? Where's the t to the 1/3? There's just this mess. Okay, so one big simplification is to think that the thing's actually just a height function. So there's a substrate called x, which is the real line, and above that there's an actual height function, and it's evolving. Okay, that's a big simplification. And the physicist's favorite model of how that evolves is this Kardar-Parisi-Zhang equation. Okay, so what's this Kardar-Parisi-Zhang equation? It's a stochastic PDE, and it says the height function is growing by 3 basic mechanisms. Okay, the 3 mechanisms are, well, okay, we're all used to this space-time white noise forcing. And that's just because you can think in that Eden model where the thing that's forcing is sort of independent from different sites in time and space. Okay, so that's reasonable, that this should not have long-range correlation. And we'll just assume there are no correlations in space and time. Okay, so space-time white noise is forcing it. And then there's two other terms. There's a relaxation term which kind of keeps this interface as a function. That's this thing. So this part is just a heat equation. And then the most important term is this lateral growth mechanism. Okay, so that's the key term. So why would you have this dxh squared here? That's because if you think about how the growth works in models like this, the growth is not really all up. It's just out. It doesn't know from which direction the thing's just growing. It doesn't know what's up, right? So the growth is about the same in all directions. So if you look at the vertical component of one of these little arrows, it's definitely a nonlinear function of the slope, right? So it's some nonlinear function, f. And then the physicists, they say, well, okay, what would you say about this nonlinear function? Well, it should definitely be like symmetric under plus to minus. That's about it. That's the only thing you would assume. So the physicist's idea is you just expand it. And then the first term, it can just be removed from the equation by shifting up. And shifts up don't even matter in our world because all we're looking at is this fluctuation thing. So the whole, if you think about the Eden model, the whole thing's growing way out and then you've got these tiny fluctuations in the boundary. So of course you have to scramble to get this thing back to where to see these fluctuations anyway. So height shifts, that's fine. Okay. And then this thing, well, if it was symmetric anyway, that would be 0, but otherwise you can just shift sideways to remove it. So then the physicists say, well, the first thing that comes, which we can't get rid of, is this, so that's what we'll put in the equation. And in this way, they get some magic equation. Okay. The funny thing is, if you actually just take a f of dxh, and then you say, okay, what's the meaning of a stochastic PDE? The meaning of a stochastic PDE is that you should take the noise, smooth it out, solve your PDE like classical PDE, and then remove the smoothing, and if you get something, that's the solution of your stochastic PDE. So what happens here is very amazing. If you put f of dxh, any f, and you smooth it and remove the smoothing, it says, no, I would prefer to be a square. It doesn't matter what the f is. That's a recent result of Martin Hare and me. So it's the only, it's sort of a canonical model in that sense. Okay.
May I ask you about
Yes.
space-time white noise? Because space-time, in this case, space, one may think about x, which is flat.
Yes.
Or one may think about space as being the boundary, and it's not flat. So since space-time seems to be sort of uniform, should I think about this as uniform, in the flat sense, or uniform on that funny boundary?
Yeah, that's a good question. It's not supposed to matter. In principle, it should matter. I think it doesn't matter because of the sort of crazy universality of this world. But it's a good question. So if you did that, you would have a slightly more realistic model, which then presumably on large scales would behave the same as this one.
But I just wonder if it would make any difference with scaling and so on, right? Because I mean,
It's not supposed to make any difference. It's not supposed to make any difference, but you would have a hard time writing the thing down. Good. Okay. There's actually another question which is related to that, which is that you might actually want the noise to be, instead of looking at t and x, you should look at h and x. That's a model the physicists actually care about.
This is what I was saying, I think.
Yes, sort of. Yes. Is it exactly what you were saying?
Well, close enough.
Okay. Yes. So the answer is that that thing is a strange thing. I can show you. It has some weird behaviors which are a bit different, depending on the regimes. Okay. Okay. The status of that is that Martin worked extremely hard and claimed he can prove that it makes sense, but the proof is so complicated he's not going to write it down. Okay, here's a model I'm actually going to talk about. This is TASEP, and TASEP is this funny discretization of KPZ. So in TASEP, the height function is just replaced by this, it's just a lattice down here, and don't worry about these guys yet. And it just goes up or down one at each thing. So it's a simple random walk path is the height functions, okay? And the rule in TASEP, and as I said, don't worry about the particle. Oh, okay, so the simple random walk path, you can just code it by particles. So whenever it goes up, you say there's a particle. And whenever it goes down, there's no particle. That's just, so you can think of it as particles and no particles, or as height and simple random walk paths. Okay, and then the whole rule is that if you have a peak, it jumps to a valley at rate 1. That's all. So there, it jumped. That's it. Okay, so I'll go back. This is not. I'm just showing you the movie again. This little peak here is going to jump to a valley, and you see that's the same thing as a particle jumping to sideways. And it also is the same thing as the particle can't jump if there's somebody in the way. So that's why it's the totally asymmetric simple exclusion process. Okay, so that's the whole thing. That's the whole model. Okay, now you may not believe this is a discretization of KPZ, but the rate of jumping down is just -2 the indicator function of having a peak, right? And then you just do a little calculation with plus ones and minus ones, and that's exactly this. So it's exactly a discretization of KPZ. You see? This plus and minus derivatives, that's just h of x plus 1 minus h of x. And this is h of x minus h of x minus 1. It's just an exact calculation. Okay? And then there's also a funny thing. You see, this guy's jumping down. And you see this thing, this is dxh squared. So you thought KPZ was going up, but it's going down. But that's because if something's going down and then you move it up, it could look like, it's very hard to tell what's up and down if you're doing this global height shifts. Okay. Now, one of the things we know about KPZ, let's go back to KPZ for a sec, is that Brownian motion is invariant for KPZ. Okay? And all the invariant measures are just Brownian motion plus a straight line. Okay? That's what the invariant measures are. And of course, that's why it's so hard to make sense of this equation, because if you have a Brownian motion, then this thing is very hard to make sense of. Actually, you have to subtract an infinity. But okay. Here, symmetric random walk is invariant, except for the height shift. So you start with a symmetric random walk. Later, you'll see a symmetric random walk, but maybe it's shifted. Oh, down. It'll be shifted down. Okay.
You say that the symmetric random walk is you're talking about a single particle, or I mean.
No.
What do you mean the measure, invariant measure?
Forget the particles. The particle is just a little picture for me to show you something later. I take a symmetric random walk, and I run TASEP, and look at some time later, and it's still a symmetric random walk. It's the invariant measure of the Markov process of the height function.
The height function is not negative.
No.
No. Oh, okay, because it doesn't.
Oh, no. Is that okay?
Yeah.
All right. Okay, so now TASEP, one can do some calculation. I'll show you later how you do these calculations a little bit. And what was known. So all these results are from the early 2000s with people like Johansson and Spahn and Borden, and Sasimoto should be there too. Oh yeah, Sasimoto. Okay, so you take this initial condition, okay, the corner because so it's all particles on one side and all holes on the other side. So it just looks like this. That special initial condition. It depends like crazy on the initial condition. And then you run it, and you can see after a while it's going to look like a parabola. Okay? Actually, I'll even show you it. Here's what happens. Okay. Sorry, this guy's in the way. I don't know how to get him out of there. Okay, anyway, I'll run it again. Okay, so you start it. Oh, sorry, the movie's upside down, but anyway. It's the same thing. So you run it, and you see it makes a parabola, and then there's this fluctuation on top of the parabola. Okay. All right. So where's my thing? Okay. Okay, so you get this thing. And now if you look at the height function at some time t and x, well, it looks like some constant times t. The constant's negative. It's going down. Minus a parabola. Okay. And then there's this t to the 1/3 fluctuation. But the fluctuations themselves are given by this Tracy-Whittem distribution, GUE. This is actually the same thing you get if you look at a GUE matrix, which is just a n by n Hermitian matrix full of Gaussians to the extent it could be, independent Gaussians. Okay, so they're complex Gaussian IIDs above the diagonal, real Gaussians on the diagonal, and then flip it to get the other ones. And now you look at the top eigenvalue and you rescale it in a similar way, then you get this GUE Tracy-Whittem distribution. This is just some special distribution. It's given by some special functions, or alternately by some Fredholm determinants. Actually, maybe I'll show you the formula for it. So FGUE of, say, A, this is a probability distribution function. It's given by determinant of I minus K on L2 of A to infinity. That's where the A comes in, where K is a special kernel. K is an operator defined by its integral kernel, which is this one. See? Okay, and area is the area function. What's the function looks like? Did that define the function enough? Okay, it's the solution of area prime u equals u. Okay. Okay.
Looks like it's not the first time you've drawn this.
Well, I drew it yesterday. Okay, fine. Okay, and then if you start from flat, now flat just means particle, no particle, particle, no particle, particle. So it just goes like that, and then the thing just goes down, and now there's no parabola. So you get these t again, and then actually C3 and C1 are the same. That's just a coincidence, and then t to the 1/3, but you get the GOE Tracy-Whittem distribution. So it's the same thing, except it's a real symmetric matrix full of IID Gaussians to the extent it could be. And you look at the top eigenvalue, and you get some distribution which kind of looks like that one, but it's not the same one. And it has its own K, which I won't write. That's the only difference. There's some funny code which tells you your initial distribution comes into a code in the K. Okay?
What's amazing is how the ratio of those two distribution functions comes up.
The ratio. Why?
You have FGUE divided by FGUE.
Oh.
Because you divide the interval by the orthogonal matrices.
Okay. Very good. And this is one of the rare results of mathematics which is actually checked in physical process. So this is a liquid crystal. It's about 1 centimeter wide. And Takeuchi in Japan, he can actually make this thing essentially do the Eden model. So there's two phases of the liquid crystal. There's the dark phase and the light phase. And he fires a laser beam, just like this one, into the middle, and then it expands. And this is very, very repeatable. So he can do these experiments. And then he takes a laser beam and he puts it through a lens. So he fires a big line, and that makes this thing, and then it grows up. And he can check, and one looks like GUE and one looks like GOE, at least to a few moments. It's quite an impressive experiment. Okay. Okay, now there's more. You can actually look at the processes you get. So here, we're going to look at the process which is the difference of the parabola from this wiggly line. And that's this thing called the Airy-2 process. Okay, it's a spatial process, a special stochastic process. its finite dimensional distributions are just given by some formula, right down in a second, which is just a generalization of this formula. And again, if you do it starting from a straight line, you get a different process called the area 1 process. And it just has a different formula. So what do these formulas look like? Well, essentially, maybe I'll draw it on the blackboard. The formulas have the following nature. You want to know what are the finite dimensional distributions, the probability that one of these processes, A of xi is less or equal to ai, I equals 1 to n. You want those finite dimensional distributions, and that will define the process. And they're also given by Fredholm determinants, but now you look at the product I equals 1 to n of L2 ai to infinity, and your kernel becomes a matrix version of this kernel. Okay, an n by n matrix valued operator. So I'll just show you that one. And so to each one of these initial datas, there's a special matrix kernel, and it's just full of all this complicated stuff. And wow. Don't read it too carefully, just to get some idea. Because basically, this is just the result of having some exact formula in TASEP, which I'll try to show you in a second, and then you take the scaling limit, and there's no rhyme or reason to the thing. I'll try to show you some rhyme or reason as we go. Okay, so that's those are the results you had around 2000. Okay. Oops. Now what's really going on behind all this? Okay. So what's really going on is in all these models, you've got this scaling. Okay, it may not have been so obvious, but what you should really do is put a small parameter epsilon and rescale your height function like this in all cases. Okay, this is called 1, 2, 3 scaling. And every model in this universality class, in principle, is under this 1, 2, 3 rescaling, supposed to being rescaled to some universal Markov process, which is going to govern the fluctuations of everybody. And that's the KPZ fixed point. So KPZ itself is not scaling invariant. If you take KPZ equation and you rescale it, so you take this 1, 2, 3 rescaling, and you take the KPZ equation, you're going to get this equation. You're going to get, okay, you get dth equals dxh squared. That part's invariant, but then you get plus epsilon 1/2. You can just check this yourself. It's not hard to check. So it's not scaling invariant. It gets epsilons in front of the stuff which you're familiar with, the heat and the noise. Okay. So in a sense, the KPZ equation is no more canonical than TASEP or any of these other models which people have been able to study. Okay? And then there's all these other models when dreams are going to actually converge. Okay. Now, there's actually another fixed point in this world of Markov processes, which is the Gaussian fixed point. In physics, they call it the Edwards-Wilkinson model. How they got their name on it. I think we've seen this guy in our lives before, and you didn't know it was called Edwards-Wilkinson, but now you do. Now, it has this scaling invariance. This 1, 1, 2, 4 scaling invariance. Okay? And it has its own little tiny universality class of models which will scale to it. For example, if you took symmetric simple exclusion, where the particles jump both ways, and that just means the height function can jump up just as often as it jumps down, okay? That model has an extra invariance over the TASEP. It has an h to minus h invariance, and it has a t to minus t invariance. Whereas TASEP only has an h to minus h and t to minus t invariance together. That extra invariance means it sits here, and when you rescale it, it actually just goes to this Gauss fixed point. Okay. Now, on the other hand, what one could do is one could take a model which was close to this stable manifold for the Gaussian fixed point, somewhere here. Okay? And you could rescale it and tune the nonlinearity as you go along, as you rescale. You see, if you just take a slightly asymmetric simple exclusion process, and you rescale it with this scaling, it's just going to go flying up to here. Everybody just flies up to there. But if you tune the asymmetry to be small as you do this rescaling, so actually you make the asymmetry epsilon 1/2, then it'll sort of move along here. You'll keep it close to here, and it goes to the KPZ equation. Okay? So now you're going to see a lot of results because Martin proved that the KPZ equation makes sense, which in principle, what it really is a way to approximate the KPZ equation by things, showing that all sorts of models which have a tunable asymmetry, which TASEP doesn't, right? In TASEP, you don't know how to tune the asymmetry. But in some of these models, you can tune the asymmetry, and so you can tune that asymmetry to be small as you do this rescaling, and you're going to get the KPZ equation. So there's tons and tons of papers coming out doing that now. Okay? That's the blue. That's the little universality of the KPZ equation. Okay? But the real universality is up here, where everything rescales to the KPZ fixed point under this pure scaling. Okay? The only problem with this is that people could see that this was the right picture, except nobody could tell what's the KPZ fixed point. So it's kind of an empty thing. Okay, so all we had was these few self-similar solutions, because the only thing you could solve were these special initial conditions. Okay, now, if you want to know why is it difficult to figure out what's the KPZ fixed point? Well, okay, it's the same thing as there. Let's take KPZ. So one of the nice things about KPZ equation is you can just, rescale. You can write an equation for H epsilon, which if you do it with TASEP, it's going to be a very complicated thing, right? Okay, so the epsilon will come here, and of course, if you want to know what's happening as epsilon goes to 0, which is supposed to be this KPZ fixed point, everyone just look at this equation, and of course I should just remove that part, right? It's pretty obvious what you should do. The problem is, so you get, so you just get dth equals dxh squared, right? The problem is that's called Hopf's equation. Or if you take u equals dxh, it's called Berger's equation. That's Berger's equation. The problem is that equation is not an equation. The problem is Berger's equation is not a well-posed thing. When people talk about viscosity solutions of Berger's equation, that's just because they're picking out some special solution. In fact, if you perturb Berger's equation by epsilon of viscous stuff, and let epsilon go to 0, or you perturb it by epsilon of dispersive stuff and let epsilon go to 0, you don't get the same answer. And now we're perturbing it by epsilon of this kind of stuff. So it's just we're getting a third answer. Okay? And there's no way to characterize it. Even this problem, after all these famous people worked on it, all they can tell you after 30 years is if I have a bump, I can tell you what's the limit. And then, oh yeah, maybe some guy knows if there's 2 bumps or something like that. Okay, it's really that bad. Okay. Now, you can just check the dissipationless limit. The viscosity solution have an exact formula. It's this Hopf-Lax formula. You could just plug in Brownian motion, and you could just check you don't get Brownian motion. So this can't be the limit. It's not that. It's something more complicated. Okay. So one of the problems with the KPZ fixed point is that you can't tell what the limit is by writing down an equation, because there's no equation. There's no stochastic PDE. There's nothing. So the only way it could be done is by actually just solving one of the models and taking a limit. So what we are able to do is we just solve TASEP, and then we take a limit. Okay. So what I'll do, so solve TASEP means we computed the transition probabilities of TASEP completely. And the formula is a little bit complicated, so what I want to show you first is the fixed point version of the formula. You take a limit, and in the limit, the formulas are a little bit prettier, of course. Okay? And you can just think of whatever the answer is for TASEP, and I'll go into it a little bit at the end of the talk. What they are is just discrete versions of what I'm going to show you, where Brownian motions are replaced by random walks of a certain type. I'll show you a little bit, but you'll see it's a bit complicated there. Okay. Okay, so what's the KPZ fixed point? Okay. So first of all, I have to tell you, it's a Markov process on some state space. And it's not natural to take the state space to be the space of continuous functions. Why not? Because if you think about this initial data, which was one of our basic initial datas, we're rescaling like this. Right? That, forgetting time, that's our rescaling. So that thing gets narrower and narrower and goes to this. Right? And that's not convergence of continuous functions. Actually, physicists, they sort of know this. So they're great. They have a name for everything. They call that narrow wedge. That's what it is. Okay. So we have to include narrow wedge in our space of functions. And the natural way to do that is to just have the space of upper semi-continuous functions. So narrow wedge is the function which is 0 at 0, if you like, or wherever, and minus infinity elsewhere. And that's a perfectly good function in our world. And in the sense of interface growth, it's very natural because this thing will sort of grow to this, right? Because everything's growing out. Okay. So actually, UC is really the natural space. Now, the upper semi-continuous functions, remember what upper semi-continuous means. It just means that if you take the lim sup as you're going to a point, it's less than the value at the point, less than or equal to. Okay. There's a better definition of upper semi-continuous. It's that if you take the hypograph of your function, the hypograph is just you draw the graph of your function and take everything below it. Then that should be a closed set. Okay, so upper semi-continuous functions are functions where the hypograph is closed. Closed sets have a nice topology, the Hausdorff topology. So that's the topology on upper semi-continuous functions. Okay. Okay, so that's the state space. And the transition probabilities, so if I start with an initial data, then what we have to tell you is the probability that the height function at time t at some points xi are less than ai, right? And they're given by a determinant of some operators. What kind of operators? Well, you know, here's the definition of the Fredholm determinant, but okay, don't look at it. Here's a better definition. A determinant is just the product of the eigenvalues, right? So if you take a determinant of I minus an operator, it's just the product of 1 minus the eigenvalues of that operator. So it's the product of 1 minus lambda I. Okay? So if you want that to converge, you need the sum of the absolute value of lambda I to converge, right? So that means that if you want this thing to make sense, you should insist that the trace of the absolute value of the operator be bounded. The trace of the absolute value of the operator is the trace, the trace of the absolute value of the operator. That's the positive symmetric square root, and that's called the trace norm. And that's a norm on operators like L1 norm. Okay, so it's like the L1 of operators, and as long as they're in this trace class, this thing converges, and in fact, the determinant is a nice continuous function on the trace class. So in other words, there's supposed to be a code which tells you if you're given initial data, here's a trace class operator, and I produce for you a trace class operator for your initial data. And that's what I'm going to show you. Okay, so here's the code. Oh, yes, okay. So the code is this Brownian scattering transform. Okay. So you take your function, h, and you look from minus L to L, and you send a Brownian motion from U. Okay, I call them U1 and U2. U1 to U2. U1 and U2 are like the U and the V of the operator. They're the parameters in the operator. We take a Brownian motion. We are starting at U1. Okay, so now it's a Brownian bridge from U1 to U2. And we ask that it actually crosses below the function h. This is the function h we're trying to probe. Okay? So we're going to probe the function using Brownian motions and ask what's the probability that a Brownian bridge from U1 to U2 actually hits the hypergraph of the function. Okay? That's called hit. And we'll think about it as an operator. Okay? Just think about that as the kernel of an operator. And you could ask, here's a question. If we know this guy, do we know the function h between minus L and L? Chris? I would have guessed no. Well, you do. You can recover it from P. But we have to do something much worse, because we need this on the whole line. Now, one thing is obvious, is that if you just try to take L to infinity, it's not going to work, because the Brownian motion gets blurry in the middle. So this crazy thing tells you to refocus on the center. So you run the heat equation backwards around the thing and refocus on the center. And I know you were told never to do that. But this problem is amazing. Every time it tells you to do something you think isn't going to be fair, something comes to save you. If you look at this operator, we're never actually going to use this thing. We're only going to use it surrounded by e to the td cubed. Okay? And if you look at this thing, e to the x d squared, this is the heat operator, and then t over 3d cubed, and t is not going to be 0. T could be positive or negative, but never 0. It doesn't matter what the sign of x is. It has this beautiful kernel. It's a beautiful operator. So whenever I write a backwards heat thing, you don't have to worry. There's this thing there to save you. Okay, so we take this p hit, and you take this thing, and believe it or not, there's actually a limit. The limit, of course, acts in a horrible space, but surrounded by these guys, it's all fine. And that's the only thing we'll ever use.
So your point is that you could put a negative x in this formula.
Yes. It makes no difference whatsoever. It's actually a group. As long as t's not 0, this is a group in x. It's funny. Okay. So this is going to be our kernel. Okay? Okay, so this just repeats that. Now, you actually have to extend the kernel a little bit, because remember, it was supposed to be a matrix. There's all these xi's, and you're supposed to have a matrix-valued operator. And so you extend it by just running heat equation backward and forward around it in this crazy way. Okay, so here's the theorem. It should say theorem. This is all completely rigorous. If you asked me before we did this whether any of this could be true, I would have said it's impossible. But all of these things are just proved by taking limits from an exact formula for TASEP. So it's not nearly as hard to prove as you think. Okay. For any t not equal to 0, the map from UC into this thing is continuous. It's continuous from UC into the trace class. So that's, of course, quite amazing, given that you were solving backward heat equations all over the place. The Brownian scattering transform is invertible by determinants. So as you take t to 0, this thing just recovers your function. Well, actually, 2 is contained in 3. The resulting objects are Markov transition probabilities. They satisfy the Chapman-Kolmogorov equation. It's a little tricky to prove, but okay. So if they're Markov transition probabilities, they define a Markov process on the space you see. It's 1, 2, 3 invariant, and it's the, well, it should be the KPZ fixed point. Okay. It is the limit of TASEP. Did I write that? Oh, yeah, okay. So KPZ fixed point is the unique Markov process with these transition probabilities. It's 1, 2, 3 scaling invariant. It's skew time reversible. It's stationary in space. It's the limit of TASEP under this. Now I've actually shown you the numbers. You can check its path properties just from this. I mean, you know the transition probabilities. So you can just start computing. You can check it's locally Brownian and Hölder half minus in x. It's Hölder a third minus in t. And although the recipe I showed you looks a little bit scary, you should imagine that if you had some actual function like flat, you can just compute the thing. It's just, you can compute it by the reflection principle. Or if you have a narrow wedge, you can just compute it. So in all the special cases where it was known before, you can just sit there and compute. In a few seconds, you'll get the old formulas. So you get this formula just by, well, there's nothing. It had to hit something like it had to hit this. The Brownian motion had to hit this. Well, you know how to compute that. You just check and you get that area kernel. Okay. And hopefully it's the unique local dynamic satisfying these three things. Okay. Okay, so are there any question about this? Then I want to...
That's the transition was done by Tracy with many years ago, right?
What?
The transition for TASEP was...
The transition probabilities for TASEP?
Yeah, weren't they?
So let me tell you the story. No. Definitely not Tracy Whittam. Actually, it was computed by Schutz in 1997. But what he computed wasn't useful. Okay. So here's what was known. So here's the story of TASEP and how it was solved. TASEP's an old model. TASEP goes back to the late 60s. And it's been studied very, very intensively for the last 30 years. Okay, so in 97, Schutz actually did the computation of beta ansatz on TASEP, and you get the following thing. Now, you have n particles. Okay, n particles. And you ask those n particles, if they started at the vector y, so that y1, y2, y3, and you want to know if they go to x, then there's a n by n determinant to compute those probabilities. This is what you meant?
I was thinking more of the later Tracy and Whittam paper where they give the determinantal formula for the edge of the TASEP. Well, I figured it, maybe it's...
You're confusing things. I'll talk to you about it later. Yeah. They never worked on TASEP. They did something for ASEP. So trying to extend this formula to ASEP was a long-standing problem. It doesn't extend. There is something, but it's not great. Okay? It's not as good as TASEP. Okay. So anyway, it's some n by n determinant. There's some crazy function given by some contour integral. Okay. Don't read this too carefully or you'll just get more annoyed. But there's some contour integral defines some function, and that function goes into the thing, and that's the formula. That's the formula. And nobody could do anything with this formula because it's just for n particles to n particles. And of course, we need infinitely many particles to 5. That's our problem. Okay? So that would mean that you would have to make some enormous summations over all the other particles and take the n goes to infinity limit, and nobody knew how to do that until Sasimoto had an absolutely fantastic idea. So he realized that because of some magic properties of this function f, I won't go into this thing, but f satisfies some amazing identities, which allowed him to rewrite this formula as a sum over Gelfand-Zeitlin patterns. And then he realized that that thing was actually a signed determinantal point process on the space of Gelfand-Zeitlin patterns. Now, once you have a determinantal point process, if you want to know the probabilities that you're just less than some few things at some time, there's this Eynard-Meta theorem which comes to save you. Okay? So that was around 2006, and let me tell you the result of all that. The result of all that is the following theorem of Borden and Sasimoto and these other guys. If you want to know the probability of the TASEP, and now it's in terms of the particles, but you know, the particles to the height function is sort of the same thing. It's just essentially an inverse function. So if you know where the particles are, you know what the height function is. Okay. This is given by a determinant, of course, of the type we're talking about. And the K is given by a recipe. The K is given by this thing. Now the Q is just some funny matrix. It's a matrix with just ones either above or below the diagonal. I never get it straight. And okay, so this is just something. Don't worry about that. But the key part of the kernel is this. Okay? So the key part of the kernel is these psi's and phi's to make the kernel. The psi's are given to you as some sort of contour integrals, which is a little bit like the previous one. It's not exactly the same thing, but it's essentially the same thing. But the important thing is the phi's. You don't know what the phi's are. The phi's are given to you implicitly. You're supposed to find phi's, which are biorthogonal to the psi's, and are polynomials of certain degrees. And then you get to do this. Now, I didn't write this thing very well. I should tell you what these psi's really are. Okay. You take Poisson measure on the positive integers. So, you know, t to the n over n factorial, e to the minus t. Okay. And now you take orthogonal polynomials with respect to that measure. They're called Charlier polynomials. Okay. This guy here is just the Charlier polynomial shifted by the initial data. Okay? So the Charlier polynomials are orthogonal polynomials with respect to the Poisson distribution. And the psi's are just, did I say they were just the Charlier polynomials shifted? They're the Charlier polynomial times the Poisson measure shifted by the initial distribution. And now you're asked, so you've got some orthogonal polynomials, and you're asked, if I shift part of the thing, what are going to be the new biorthogonal polynomials? That's the actual problem. I'm sorry I didn't write it out here. And you say, oh, that's easy. I'll just shift the thing, and then that'll be the answer. Right? Now think about it for a second. It's not going to work. So if you take orthogonal polynomials, and you shift one half of the problem, and you ask what are the new biorthogonal guys, just shifting doesn't work. Well, it works in one case. If the shifting is by something evenly spaced, then by magic it works. And that's why they only knew this case and flat. Otherwise, there's a problem nobody had the slightest idea how to solve. So it was sitting there for 10 years. About 10 years? Yeah, I guess 07 to 10 years. Nobody had the slightest idea what would be these biorthogonal polynomials. So we found them. So we have a general formula for the phi's. So the phi's, believe it or not, is the probability that a geometric random walk first hits the curve of the x's at k. And it's not obvious in any sense. Okay, so these are the examples that we know. Okay. Okay, so here's the theorem. The phi's are just given by, these are the psi's. These are the ones you knew. Don't worry about that. You can sort of write them like this, where that's the q. What are the phi's? These are the mystery guys. So the mystery guys, up to this funny, simple thing, are just HKs where HK solves this backwards heat equation. So the backwards heat equation, well, why do I call it backwards heat equation? I'm going to think of Q as the transition probabilities of a geometric random walk. Now that doesn't really look like it, does it? But in this problem, because it's a determinant, you can conjugate by anything you want. So you can conjugate by the function p to the x, if you like. And then this is just p to the y minus x indicator function x greater than y. So they're the transition probabilities of a geometric random walk. So this is sort of free if you want. Okay, so this says you're solving backwards, not the usual way. That's the important thing. You're sort of running a geometric random walk problem backwards in time with at the late time a sort of 1 there, which sort of says you hit at that time. And the function is 0 along the boundary created by these x's. N is just a parameter which says where you're looking in the whole problem. Okay? Now, believe it or not, this is a backwards heat equation that looks like it shouldn't make any sense, but this Q inverse can be computed, and it has a kernel which has dimension exactly 1, which means every time you go backwards, you have the freedom to adjust to have this maintained. So the problem's perfectly well posed at the discrete level. Okay? And I claim this problem is just the problem, once you unravel the things, the problem is just the problem of starting a geometric random walk and asking that it first goes above this curve at time k. And n, as I said, is just a parameter to say where you were looking. Okay, so there's the definition. I want to prove to you they're bi-orthogonal. So here's the fun. Okay, the proof is unbelievably easy once you realize this thing's true. How much time do I have? Like a minute? Negative a minute? -5. Ah, okay. Okay. I'll stop at this slide.
4 minutes.
I'll stop at this slide. Okay. Because this is it. This is how you solve TASEP. Once you've done this, the rest of it just follows. And the proof, this is the whole proof. The problem was guessing the answer. So I've got the psi's and the phi's. And the psi's are just given by this formula. And the phi's, I claim, are given by these HK's, this. The point is when you do this summation, because of this e to the minus t over 2 grad minus and e to the t over 2 grad minus, that contracts the variables. You can sum over the z, and that means that z1 is z2. So you just get this. But this q, from the definition of the h's, just shifts the h around. And it's looking right at the boundary. So at the boundary, it's either 1 or 0, depending if you were right at the end or not. And that's the whole proof. So it's just, I just wanted to show you this because it's unbelievably simple to check. And then all those amazing results just come from rescaling all this stuff. I'll stop.
Questions or comments?
So I just want to make sure that that whole story about functions that were upper semi-continuous, well, in the end, in some sense, is irrelevant because it proved to be much more regular than that, right? Because you said that it's held there in time.
That's right. But the thing is that those special, it's like an entrance law from bad stuff. That's right. But the thing is, those aren't bad stuff. They're like, you should think of those as like the delta functions of this world. So you really want to start, they're like the fundamental solutions. So you want to build things from them.
But then it's sort of smoothed out.
Of course, immediately, yeah.
Yes, I'm interested when you point at this picture and then you write that, But you don't go back to this picture and explain how that fits.
Because I was 5 minutes over time. so,
But
so,
exactly,
so,
question period gives you an excuse to do
yeah.
Thank you.
So I need a working one of these. Okay. So there's the phi's and the psi's in that formula. You have so microscopically, it's a geometric random walk, and the curve is given by this x's. Okay. There's the first part, which is the phi's, and that goes to here. And then k is the hitting time. And then after that, you see the psi's are just q. Okay, it's a weird world. It's q to the minus l. So you just run the random walk backwards in time until it gets to there. Don't worry about backwards in time and forwards in time. You have to get used to that. That's because of these e to the. You see, the thing wants to run normal random walks, but then refocus always. So every walk looks backwards in time. So that's why it's q to the minus l. You should really think of this q to the minus l as there's a box of size L. No, okay, unfortunately there are two things called L here. There's a box of size big L. And this should really be q to the big L minus L. And then outside of this whole picture, there's a q to the minus L, which tells you to refocus. Okay? And then so this is the phi k. It goes from here to here at k. And this is the psi. He's free, right? After it hits, it's just a free thing. Okay? And the h is really just this hitting probability, except for one little thing I didn't tell you, which is that it had to be a polynomial, and hitting probabilities aren't polynomials. So you have to take a polynomial extension of the thing. Okay. Turns out it's not that hard.
Okay, well, let's thank Jeremy again.